Our next speaker is Dr. Laura Grigori, who is joining us here from the French Institute for Research in Computer Science and Automation, INRIA. She leads a joint research group between INRIA, University of Pierre and Marie Curie, and the National Center for Scientific Research. Her field of expertise is high-performance computing, numerical linear algebra, and combinatorial scientific computing. She's co-authored many papers introducing communication-avoiding algorithms that provably minimize communication. And it's been my pleasure to know of her work personally and have it influence the research in my lab. She is leading several projects now in preconditioning, communication-avoiding algorithms, and numerical libraries for large-scale parallel machines. And now she's going to be giving us her talk on fast and robust communication-avoiding algorithms, current status and future prospects.
Thank you, Padma. Thank you for this introduction. I'm very pleased to give this talk today because that's the conference where we published one of the first papers on communication-avoiding algorithms. And my talk will start with our motivations, then I will briefly review some past work on reducing communication, then I will introduce some new results on communication complexity of linear algebra operations. Then I will discuss some of those new algorithms that we refer to as communication avoiding that minimize communication. And I will briefly describe two algorithms, the ALU and QR factorizations. Those algorithms are progressively implemented in libraries like ScaleAPAC or LAPAC and sometimes in vendor libraries. And then I will discuss also how do we avoid communication in sparse linear algebra by focusing on two operations. The first one is a sparse low-rank approximation, and the second one is solving linear systems by using Krylov subspace methods. So our motivation is a large gap which exists in between the time required to compute one floating point operations and the time required to transfer data, either in between different levels of the memory hierarchy or between different processors. And later on, I'll discuss some implications of using non-volatile memories as a secondary storage. But for now, let's focus only on network and DRAM. And that's an old problem. Already in '95, Wolf and McKee mentioned that we are going to hit the memory wall unless something basic changes. And different studies afterwards showed that the gap is steadily and exponentially increasing over time. And here I'm showing some data which is based on a report from 2004, Getting Up to Speed, the Future of Supercomputing. And they're looking at data from '95 to 2004. And they observed that the time per flop was improving at 60% per year. But if we look at the bandwidth or the latency, the bandwidth is improving only at 20 and something per year for both network and DRAM. And the latency is improving only at 15% per year for the network and only at 5.5% per year for the DRAM. So now let's look at some more recent data. And so let's look at, for example, at the DRAM latency of two generations of double data rate memories, second generation and fourth generation. And you can see that in 7 years, there was an improvement of a factor of 2.56 only. So going from 120 nanoseconds to 45 nanoseconds. And the stacked memories, they seem to have similar latency as the DDR fourth generation. And if we look at the time per flop at two different Intel processors, you can see that in 9 years, the time per flop per chip decreased by a factor of 18. So a huge gap in between the DRAM latency and the time required for a floating point operation. And so basically only from those data points, you can see that the time per flop, an annual improvement roughly would be less than 40%. So it changed since the previous data up to 2005, which is somehow expected. But still, we have orders of magnitude in between those two times. And basically, the time to fetch from DRAM 1 byte of data, a processing unit could compute in 88 6 flops. If we look at 2004, it could compute over 100 flops. And if we look today, a core could compute 900 flops. So orders of magnitude difference. And the same trend can be observed from the interconnect. the time to receive a small message from another processor, one single core today could compute thousands of flops. And there is really no solution from the hardware community inside, which means that we do need to address this problem at the software and at the algorithmic level. And different approaches in the past looked at this problem as a scheduling or a tuning problem. Tuning means that you try to overlap as much as possible communication with computation, but if we look at numerical linear algebra operations, we can get only a factor of 2 speed up, so that's not sufficient. Another approach is to change the schedule of the computation, and for numerical linear algebra, we call those algorithms block algorithms because you try to express your algorithm by using operations on matrices instead of operations on vectors. And one of the first algorithms in linear algebra was introduced already in the 60s by Baron and Sunat Dyer. And that's the algorithm for computing an ALU factorization that we have used in LAPAC and ScalaPAC for almost over 50 years now. And what you can see in the plot here, it's a performance on a model of an exascale machine in which we increase the number of nodes and we plot the ratio of computation to communication when you compute the ALU factorization of dense matrices. And the plot is divided in 2 regimes, a regime in which the computation dominate, and so the algorithm would be scalable, and the second regime in which the communication dominates. So if you look at strong scalability, for a given problem size and increase the number of processors, you reach very fast the regime in which the communication dominates. So the progress achieved so far is not sufficient. And what we need is a paradigm shift in the way in which we design our algorithms, which now need not only to reduce flops, because flops are cheap but not free, but we also need to reduce communication. And those communication avoiding algorithms do provide a fresh perspective for numerical linear algebra because they minimize both communication in terms of both volume of communication and number of messages. So they address the latency bandwidth problem. And very often we change the numerics. So we have to pay attention to the stability of those algorithms. But we do have more opportunities for reducing communication. So in terms of communication complexity, we started from results from Hong and Kung, which was proving that if you multiply 2 matrices, which are dense, and so you perform 2n³ floating point operations, and you have a fast memory of size m and a slow memory of very large size, then when multiplying those 2 matrices, you have to communicate a number of words which is proportional to the number of flops divided by the square root of the memory size. So then those results were extending to the parallel case by Aroni, Tishkin, and Toledo in 2004. And it's also easy to show that you can extend them to get a lower bound on the number of messages, just by dividing the lower bound on bandwidth by m, because the size of your message cannot be larger than the size of your memory, which is m. So then it's easy to see that those same results apply to the ALU factorization, because when you take this matrix and you compute its L and U factors, you have to multiply those 2 matrices A and B. So lower bounds on communication on matrix multiplication do apply to ALU, and it was shown later that those bounds apply to almost all direct linear algebra. So now that we have the bounds, we are able to go over different algorithms as they are implemented in ScalaPAC and see if they minimize communication or not. So I will look here only at parallel algorithms. And in this case, the memory per processor is going to be n squared divided by p, where n squared is the size of my matrix and p is the number of processors. And in this case, the lower bounds become the ones which are displayed here. So the volume of communication is lower bounded by n squared divided by square root of p, and the number of messages is lower bounded by square root of p. And that's important, which means that in terms of number of messages, we don't depend on the matrix size, but only on the number of processors. And so we are able to go over different factorizations, ALU, QR, or rank-revealing QR. And we are able to show that all those algorithms which we use for many, many years do minimize the volume of communication. So they do the best in terms of volume of communication, but they exchange too many messages. And why is this? Let's look first at the ALU factorization, which is this block algorithm from the 60s. And it goes block of columns by block of columns, and at every step of the factorization, it will compute the ALU factorization of a tall and skinny matrix, and then will update the trailing matrix. And the latency bottleneck lies in the factorization of a tall and skinny matrix. Because for stability, ALU will perform partial pivoting. So we look for the element of maximum magnitude at every step of the factorization, permuted to the diagonal position before proceeding with the factorization. So basically, you need the reduction for every column in the matrix, and the overall number of messages is going to be proportional to the number of columns in the matrix. So it cannot attain the lower bound, which is only square root of p. And the same happens for the QR factorization, and now it's because in this tall and skinny factorization, you have to compute the norm of a vector, which is distributed over many processors, so you have to have a collective communication for every column in your matrix. And the new algorithms which we introduce, which are called communication avoiding, introduce different strategies for pivoting. For example, for ALU, we have to use something which is called tournament pivoting. For QR, we have to use a different representation of the Q factor. And for the rank revealing QR factorization, again, we have to use a different pivoting strategies. So we have to change the numerics. And let's look at how do we do for the QR factorization of a tall and skinny matrix. So the main idea is to perform this operation as a reduction operation, and at each step of the reduction, the operator is going to be a QR factorization. So we start with a matrix which is distributed over 4 processors in this example. We first compute a QR factorization locally, and that's where most of the flops take place. And then we combine 2 by 2 the results, which are 2 upper triangular R factors. And every time we annihilate the elements below the diagonal until we obtain the final R factor. So in terms of messages, we have to exchange only log P messages. So we don't depend on the size of the matrix, only on the number of processors. And this algorithm is fast also because most of the computation takes place sequentially. And you can use whatever is the best sequential algorithm for the QR factorization. And when we use this algorithm to, what changes here is the algebra. So if we want to minimize communication in parallel, we use a binary tree. If we want to minimize communication in sequential, we can use a flat tree. So basically, the shape of the tree could be chosen depending on the underlying architecture. And the algebra will change. So if we would use a classic QR factorization, the algebra will be written simply as W equal QR02. If you want to use this tall and skinny QR as a reduction operation, then the algebra will be slightly changed, which means that the Q factor is represented implicitly. And if we use TSQR to compute the QR factorization of a more general matrix, it means that when you update the trailing matrix, you have to follow the same shape of the reduction trees that we used during TSQR. But we also know to recompute and recompute the Q factor as in a classic factorization. So we can compute this TSQR fast, then rebuild the Q as in a classic factorization, and then update the trailing matrix as in a classic algorithm. So this makes changes in the algorithm much simpler. You can just replace the factorization of a block of columns, and everything remains the same. And in terms of performance, we look here at the performance on 2 different Cray machines. And we look at a problem which is very tall and skinny. It has only 32 columns. And we increase the number of processes. And we look at TSQR, which is in red, which is higher. It means it's better because we present the flop rates. And then the green line corresponds to the QR factorization from ScalaPack. And then the other lines correspond to the performance you would get when you also want to reconstruct the Q factor from the classic factorization. And what you can see here is that we get good speedups for TSQR, so up to a factor of 6 or 7. And as I was saying, it's coming not only from minimizing communication, but also being able to use a much faster sequential algorithm. And if you want to reconstruct the Q factors in a classic factorization, then we still get a good speedup in between 2 and 3 on both architectures. Now let me move forward and look what happens in the case of ALU factorization, because here everything remains very stable. This QR factorization is essentially unique, so you can change the way you compute the factors, but you still get an algorithm which is numerically stable as a classic algorithm. If we move to the ALU factorization, we can write the obvious generalization of the algebra from QR to LU, we can write the same kind of factorization as a reduction, in which at each step of the reduction we do an LU factorization. We obtain upper triangular U factors that we combine them together by using a binary tree if we want to reduce communication in the parallel case, or by using a flat tree if we want to reduce communication in the sequential case. And turns out those algorithms were already known. One is called block parallel pivoting. The other one is block pairwise pivoting. And in particular, this block pairwise pivoting was already again introduced in the 60s by the same authors. And at that time, they were computing the LU factorization of a system which was having 100 equations on EDSAC2 computer. And they were using an auxiliary magnetic tape, so they wanted to reduce the number of reads and writes to this tape. And so they introduced this algorithm. So it turns out what was stable for 100 equations, it's not stable today because we want to factor matrices which are much, much larger. And the way to see the stability is to look at the growth factor, which is the ratio in between the magnitude of the elements we compute during the factorization with respect to the maximum element in the original matrix A. So if this growth factor grows linearly with the size of the problem, or in partial pivoting, it grows linearly with n to the square root of n, where n is the problem size, then the algorithm remains stable. But when the growth factor becomes much larger, that means that the algorithm is not stable anymore. You compute something very fast because you minimize communication, but you don't get even 1 digit correct in your answer. And that's what you can see here. We increase the number of processors, so we increase the number of blocks in which we divide our matrix. And then this growth factor keeps becoming larger and larger until it becomes really exponential. And that's the worst case you can see for an LU factorization. And so we had to introduce a different pivoting strategy here, which does the factorization of this tall and skinny matrix twice. So the goal is to get rows which are linearly independent, such that your elements on the diagonal are not very small, because you have to divide by these elements. And so the way we do is we perform the factorization of a block of columns twice. The first one, we just perform it to get some good rows. Then we permute those rows to the top positions. And then we perform an LU factorization with no more pivoting, so no more communication for every step of the factorization. So it's the same kind of reduction, but that's performed only in the pre-processing step, in which again the matrix is divided over 4 processors. Then locally on each processor, we select candidate rows. Then we let those rows play a tournament. And each step of the tournament is performed by doing an LU factorization with partial pivoting to select from 2 sets of rows only 1 set of rows until the final set of rows wins. And that's a set that we permute now is a diagonal position, and then we compute an LU factorization with no more pivoting. So twice the factorization, but still something which can go in practice faster. So again, we get speed ups of around 5 or 6. So twice more flops, but because we reduce communication and sequentially we perform something much faster, we can go faster overall. And in terms of stability, it gets a stability which is close to what you would get for partial pivoting. So we get an algorithm which remains stable. Now, how do we schedule this algorithm on multicore processors? So what would be the best strategy for those algorithms which minimize communication? One strategy would be to use static scheduling, and that's good because we get good locality of data. We struggle to minimize communication. Now we know how to distribute the matrix and to really minimize the communication between different sockets. But this strategy ignores noise, so whatever dynamic change in the system, it cannot adapt to it. And so this leads to cores being idle, which is represented here by white pockets, and you can see quite some of those. And another strategy would be to use dynamic scheduling. You would keep your cores busy, but you don't have any control on the data of movement which happens behind. So it would be a poor usage of data locality. And also, depending on your scheduling strategy, you can have large DQ overheads. And what works best for our algorithm, it's a combination of dynamic and static scheduling, in which we take the task dependency graph of the LU factorization, and we schedule the largest part of these tasks of this graph statically. And then only a small part of the graph, we schedule it dynamically. So threads will execute in priority all the tasks from the static part, and whenever there is no task ready to execute, it will go and pick up a task from the dynamic part. So it resembles work stealing, but it defines very well the part from which you are going to take tasks in your dynamic part. And you can see here in the middle the execution we get. So most of the idle pockets are now filled. So cores are kept quite busy almost all the time until the end, but that's normal because there is not enough work to do. And also it provides a good trade-off between load balance, data locality, and DQ overhead, which is quite limited. And it's sufficient to use only 10% of the task in the dynamic part. So you don't need much of the dynamic part to fill up the idle times on your cores. And in terms of performance here, which is obtained on an AMD Opteron using 48 cores, you can see the high is better because we present performance in gigaflops, and we increase the matrix size. And the light blue line, which is at the bottom, is a communication avoiding ALU is no optimization. So it's not sufficient to minimize communication. You also have to do more to have good scheduling strategies to be able to get good performance of the new algorithm. And then you can see the performance on MKL and plasma. And up here, you can see the performance we get with static scheduling, which is fairly good. But when you combine static and a bit of dynamic, we really get the best performance. So this turns out to be the best scheduling strategy for those algorithms. And now let me discuss a case in which you have a secondary storage, a non-volatile memory. So far, I didn't distinguish at all between reads and writes. But on those emerging memory technologies, writes can be much more expensive than reads in terms of both time and energy. So I took an example here, two different NVMs, phase change memory and conductive bridging RAM. And for both, you can see that the reads are slower by 1 order of magnitude. The writes are slower by 1 order of magnitude than reads. And also, writes are less reliable than reads. And this gap is going to be improved by new technologies, such as crosspoint or other flash memories, but it doesn't seem to be eliminated. So this suggests that in our algorithms, we should be aiming at avoiding writes when we have to use NVMs. So one case in which we need to use NVMs is a case in which you have to compute an out-of-DRAM algorithm. So suppose we have a matrix A, and it doesn't fit in DRAM. So we start the algorithm with the matrix A being distributed in a balanced way across different NVMs. And now we have two lower bounds on communication we'd like to attain. The first one is the interprocessor communication, which is as before, n squared divided by square root of p. And the second one is the number of writes to NVM. So the minimum number of writes you have to do is when you write your result back to NVM. So it's going to be n squared divided by p. So ideally, you would like to attain both those bounds, but it turns out it's not possible. So there is, for all three nested loop algorithms like matrix multiplication, LU, an algorithm must exceed at least one of these bounds. So for example, if you have an algorithm which minimizes the words which are exchanged in between processors, then the number of writes to NVM is larger by a factor of p to the power 1/3 with respect to the lower bound. And the choice of the best algorithm will depend on hardware parameters. If the interconnect if the communication in between processors is more expensive than the writes to NVM, then we favor minimizing the communication in between processors. Otherwise, we favor minimizing the number of writes to NVM. And so we can design algorithms which minimize either one of the bound or the other one. So for example, what's called a left-looking LU factorization will minimize the number of writes. We'll have to write the data only twice back to NVM. And the right-looking algorithm, which corresponds to what I was presenting before for communication avoiding LU and QR, will minimize the interprocessor communication, but will write many more times back to NVM. So as I said, the best choice will depend really on hardware parameters. Now, in the remaining part of my talk, I will focus on sparse linear algebra, and I will start with sparse low-rank approximations. That's an operation on which many researchers focus on today. And the goal is to, given a matrix A, which is very large, of size m by n, find the rank K approximation formed by two matrices, Z, W, where Z has only K rows, and K is going to be much smaller than M and N, and W transpose has K rows. And this problem has really diverse applications from our community in scientific computing when we use those approximations to get fast solvers for integral equations or hierarchical matrices, and also in data analytics for principal component analysis or image processing. And what do they have in common is that very often this low-rank approximation is used in an iterative process in which is multiplied by a vector of a set of vectors. So basically, we compute a low-rank approximation to speed up the matrix vector product. And another approximation which is interesting and also very used today, it's a CUR approximation in which you have those three matrices, and C corresponds to the columns from A, which are selected somehow well, and R corresponds to rows of A. And so the approximation remains very sparse. It preserves the sparsity of the original matrix A. And the best approximation can be computed by singular value decomposition, a truncated SVD. And that's really the best you can do, because the error of approximation, which is A minus your low rank approximation, is equal to the K plus 1 singular value of A. And the approximation is formed by the leading singular values and the corresponding right and left singular vectors. And you can see on this image, if you can compute a rank 38 approximation by using SVD, you can reconstruct the image almost, and you get an image which is almost identical with the original one. So it really works very well in some cases. You can increase the rank of the approximation, but really you don't get something which is much better. So already 38 for a matrix which has 700 columns provides you a very good low rank approximation. But the singular value decomposition is expensive. And so there are many other alternatives for computing low rank approximation, which will trade off accuracy for speed. And I will overview some of those in an order of decreasing accuracy and decreasing arithmetics, because usually those two go together, and in increasing communication going from left to right. So one of the very used alternatives is a QR factorization, the so-called rank-revealing QR factorization, which will do column pivoting, so it will communicate a lot. We also have a communication-avoiding version in which we use tournament pivoting, and we minimize communication. And something which is cheaper is the ALU factorization. So in particular for sparse matrices, ALU factorization can be 2 orders of magnitude faster than the QR factorization, because you get much less fill-in, but you have to do some pivoting to select columns and rows. And if you use the traditional pivoting like column or row pivoting, then again you will get many messages to exchange. And what I'm focusing today is in the ALU factorization with column and row tournament pivoting. And the way we do is that we select columns from the matrix A by using tournament pivoting, and then from those columns we select rows by using, again, tournament pivoting. And let me just show you, so before, another very popular approach is formed by randomized algorithms. So those seems to also trade off accuracy for speed, and we still miss today a comprehensive study of understanding when those algorithms are faster than what we know to do deterministically. So now let me focus on this ALU factorization with column and row tournament pivoting. And we suppose that we know the rank of the approximation we want, which is K. And the way we do is that we divide the matrix in blocks of 2K columns. And so the goal would be to select the K columns which are the most linearly independent, because those would be the best for the low rank approximation. And so we select locally K columns from those blocks by using an algorithm which works well, like QR with column pivoting. So we do communication, but it's only local. And then we combine 2 by 2 those 2 columns, again by using a reduction tree. Here I'm using a binary tree. And from each block of 2K columns, we select again K best columns. We put them again together until we have selected the best ones. So it's something which again uses only log P messages. And once we have selected the best K columns, We are going to select from those columns the best k rows by using the same procedure. And we obtain a factorization, which can be written as a block LU factorization. And the matrix, which is denoted S of A11, is what is called the Schur complement, which is not computed if we only need a rank K approximation. But if the approximation turns out to not be good enough, we can update this matrix, and then the algorithm will continue recursively on this Schur complement matrix until we obtain a good low-rank approximation. And in terms of good low-rank approximation, what does it mean? It means that the block A11 approximates well the first k singular values of A, while the Schur complement matrix approximates well the last n minus k singular values of A. And what does it mean to approximate well? It means that the ratio of the singular values of A with respect to the singular values of A11 bar are upper bounded by a quantity which can be seen as a low-degree polynomial in the dimensions of the matrix M and N and the rank of the approximation K. And also, we have the same ratio for the singular values of the Schur complement with respect to the last n minus k singular values of A. And so just for comparison, if you would use QR as column pivoting, the communication avoiding version, the bound would be given only by this first term here with respect to our bound. So in some sense, it's not very far in terms of theoretical bounds. And this factorization is, in fact, a CUR factorization because it's formed by these first columns of A, first rows of A, which were permuted, so identified by tournament pivoting, and a matrix in the middle, which is A11 bar inverse. And because we always use, very often this factorization is used by multiplying it with a vector, we never form the inverse. We just compute its factorization and apply it to a vector when it's needed. And what was surprising to us was to see many papers in randomized algorithms in which they really struggle with computing this U matrix explicitly. And they do use Moore-Penrose generalized inverses of the C matrix and the R matrix. But the observations that we know for many years in scientific computing is that if you just multiply as a vector, you should never form the inverse. And now let me see what we get on the same image. So in the upper part, you have the original matrix, the low rank approximation obtained by SVD, where the rank is 38 or 75. And then in the lower part, you have the result you obtain if you do only an LU with row permutations. So you see that you cannot recover the image at all. It's not sufficient to only select rows. You have to select rows and columns, or columns and rows. And then the last two images that you see here at the bottom correspond to the approximation we get by using this new algorithm. And you can see that for 38, we get some noise in the image. But if you want a higher quality, you increase the rank, you go to 75, and you get something which is very close to the original image. So it works very well on those images in which there is not so much information. Now, if we take an image in which you have much more details, like those pictures here, the SVD again will work well, but you have to use a larger rank approximation. Again, if you do only LU with partial pivoting, which is in the image here in the bottom, it's really not sufficient. You don't get any information almost from your image. And if you use our algorithm, you get something which is not as good as SVD, but still might be good enough for many algorithms in image processing. You still can see sort of half dome here, if you focus well. So now let me just compare with one randomized algorithm. So in terms of complexity, if you take a parallel algorithm which would use a binary tree, as I was mentioning before, we use only log-p messages. In terms of flops, it will be, in the sequential case, the number of flops is smaller than number of non-zeros of A multiplied by k squared, where k is the rank of the approximation. And the parallel case, you get a log factor because we use a binary tree. And now if we know that the graph is well separable, for example, it's coming from a 2D structure grid, then the number of flops decreases by a factor of square root of k. So we know how to exploit that the graph might have small separators. And now we compare with a randomized algorithm which was introduced by Clarkson and Woodruff in 2013. And that's an algorithm which is referred to as a nearly linear time complexity algorithm. And it produces a low-rank approximation in which the error in Frobenius norm is smaller than 1 plus epsilon, the error produced by the best rank A approximation. And so depending on how much accuracy you want, you choose the epsilon. And the epsilon also shows up in the arithmetic complexity because the first term in the arithmetic complexity is linear in the number of non-zero of A, while the second term depends on the size of the matrix A, which is n, and epsilon to the power minus 4. And basically, if you choose epsilon to be 0, 1, so if you want 1 bit of accuracy in your Frobenius norm, then our algorithm becomes faster because of the second term in the complexity of this randomized algorithm, which becomes very large. And in terms of performance results, we have run some experiments, again, on a Cray machine, and we increase the number of processors from 16 to 1024. We use 1 MPI process per core, and we use a binary tree. So what you can see here is that the time to just select k columns from 2 k columns, it's very small. It's 0.26 seconds for one matrix or 0.46 seconds for the second matrix. And then when you look at the results here, which present the selection of 256 columns from the entire matrix, then we get a speed up of almost 10 when going from 16 to 256. But that's not the most important part. The important part is that you can select 256 columns, get a low-rank approximation in only 6 seconds if you use 256 cores. And now if we want to compare with something which can be used today, it's hard because there is no code which will compute for you a low-rank approximation in the sparse case. And so what we are able to do is to select, by using known codes, 256 columns from a matrix which has only 1/32 columns from the original matrix. Because if we took a larger matrix, we couldn't run a sparse QR code. And so to select from this smaller matrix 256 column, we use the sparse QR code from Tim Davies and then the QR with column pivoting from LAPAC. And so the time in seconds is given here. And now if we look at the speed up we get really good speed up with respect to what you could use today. It's almost 200 times faster to use tournament pivoting to select k columns. And so now again, it's because of 2 reasons. Not only you read this communication, but also we use a QR factorization only on 2k columns. So you get fill-in, but the fill-in is only restrained to those columns. So you don't fill in all the matrix. That's why it can go fast. And now in the last part of my talk, I will briefly show some current research on how to reduce communication in Krylov subspace methods. And in those methods, we want to solve Ax equal b, and we start from an initial solution, x0, an initial residual, r0, and then we build a Krylov subspace, which is formed by the initial residual r0 and powers of the matrix A multiplied by this residual. And for stability, usually this basis is orthogonalized. And if we look at a typical Krylov solver, it has 2 steps in each iteration, computing a sparse matrix vector product. But usually the communication here is point-to-point communication because the systems we solve come from PDEs discretized on a grid, so usually processors communicate only with the neighbors. But the main problem are the dot products for the orthogonalization process, because for the dot products you do need global synchronization. And what I'm displaying here is the performance of CG from an astrophysics application in which we use really a good preconditioner, so it converges quite fast. But if we look at the time per iteration, and we increase the number of cores from actually up to 6,000, because we use 1 MPI process per 6 cores, then you can see that the overall runtime decreases But if we break down this time in between the time required for communication and time required for computation, we can see that the time for communication doesn't decrease at all. So eventually, it will dominate the overall runtime. And there are different ways of improving performance. So first two are really well studied in the literature, optimizing the sparse matrix vector product or optimizing collective communication. The third one would be to use preconditioners. That's really an important research topic, but I'm not going to cover today. And I will focus on an approach for speeding up those Krylov methods by changing the numerics. And the overall goal will be to decrease the number of iterations such that we decrease the number of global communications because we cannot get rid of the global communication. You do have to have some global communication per iteration. And we also look at increasing the arithmetic intensity. So instead of multiplying one matrix by a vector, we want to multiply at each iteration a sparse matrix with a set of vectors. And so we introduce those enlarged Krylov subspace. And the main idea is the following. We start from the initial residual. We partition the matrix into T domains, and then we split the residual to obtain T vectors. So basically, we project this initial residual on the T domains, and the first vector will have non-zeros in the first rows corresponding to the first domain, and zeros elsewhere, and so on for the subsequent vectors. And we generate a basis, an enlarged Krylov subspace, which is formed by these T vectors and powers of the matrix A multiplied by those T vectors. So at each iteration, we are going to multiply the matrix A with a set of vectors, and then we are going to orthogonalize those vectors. So we do keep the global communication, but we increase the arithmetic intensity because we multiply A with a set of vectors, and then hopefully because the solution is searched in a subspace which is larger, the Krylov subspace method should converge faster. And we have a couple of properties which shows that this Krylov subspace is a subset of the enlarged one, and the solution of the system does belong to this larger subspace. And then just let me show you some of the results we get in terms of iterations. So those are based on an enlarged conjugate gradient. We do add more vectors per iteration. So here we increase the number of vectors from 2 to 64. In theory, we would add 64, but in practice, with time, you add much less because we know how to detect the vectors we should be adding. And what happens is that the number of iterations can decrease a lot. And I will skip the following slides just to show that how the enlarged GMRS would work. The only difference would be the green part in which we would multiply A with a set of vectors, and then the following part because you have to orthogonalize more vectors than a classic GMRS. And let me go to conclusion. So those new algorithms, we know fairly well what to do in dense linear algebra because we've got those algorithms which minimize communication, sometimes at the cost of performing some redundant computation, and are often faster than conventional algorithms. We do have to do a lot for sparse linear algebra. What I've shown so far, it's still part of ongoing work. Preconditioners are an important topic that we need to address. And of course, how to go beyond. So let me acknowledge my collaborators and funding. And then the results are presented from many papers which are available on my webpage. Thank you.
Thank you, Laura. We have time for maybe one short question for the speaker. The microphones are out here if you have a question. Yes, please. Please use that. Yeah. Great, thank you.
Now, in this, you perform more than one sparse matrix vector multiplies, but the matrices are no longer dense vectors. I'm sorry, the vectors are no longer dense vectors. Is that right?
So at the beginning, those vectors are sparse because they come from projections on different domains.
But later they become dense, right?
But with time, they become dense. But the main point is that at the beginning, we have T of those vectors. Like we start with 32, but with time, we add only those vectors which are relevant. because some of them are linearly dependent of the vectors which are already in the basis.
Okay.
But then we add 16, 8, but they become dense.
Okay. Thank you.
Well, thank you. Let's thank Laura and both speakers. Thank you very much.
Thank you.